Hello, folks. Sorry I'm a little late here. Core is still ongoing. Hopefully, we'll get more people in soon, but I'm going to try to wait at least a little bit for them to show up. All right. Has everyone read the paper? I finished it up this morning myself. I'm going to assume that we've got a fairly big crowd today. People already have seen it, but I will post the link to the paper in the chat window for anyone that needs it. Go. In the meantime, I actually didn't do pull request stuff this week since I was running out of time, and I figured we'd devote most of this to the paper today anyway. But I wanted to ask, since we've got a couple of people here, Casey, are you around?
I am, yeah. What's up?
Hey, I was just curious if you had heard anything new about the Rgw stuff that we saw a little while back, those regressions.
Yeah, um, Mark just got back from break, and we talked about it in the bug scrub today. Um, Essentially, it's a lot of performance investigation around the use of timers for timeouts.
Yeah,
Seems like the upstream Beast library has some other reports of issues there, so we're going to try to learn what we can from that and participate in the upstream discussion there.
cool, cool. Yeah, I was just curious. I didn't realize Mark was on vacation. That I'm sure slowed things down a little bit. Well, good news that at least it sounds like there's upstream insight into this to some extent. All right. Well, I don't know how much longer we should wait for core people. Maybe we should get started on this. Let's see. All right. So I guess I overall like this paper quite a bit myself. I like that they went pretty in depth into explaining what they did. Um, Overall, I was a little concerned about the complexity of the system that they were testing, but they seem to do a pretty good job of isolating things. At least I thought so. Um, I found it interesting that SBDK didn't do a better job, especially when they were kind of giving it its best case scenario to run in. Um, that was yeah, just kind of overall that was my high level thought. Kind of wish that they had gotten into RocksDB results a little bit more. Oh, good, we got the core people coming. Josh, I see. Looks like cores wrapped up.
Yeah, folks should be filtering in now.
Very good, very good. So I was just kind of saying that very high level. I like the paper quite a bit. It was a good paper, Josh. Thank you for bringing it to our attention.
No problem. I really enjoyed it too. I was one. It was one place where I was linking to like a tech report where they're supposed to have more detailed results for like different media workloads, different sorts of mixes of IO sizes, and I couldn't find that. Did you see that anywhere?
I didn't. I did not. I would actually be very interested in that as well. And also, if they have anything more on RocksDB, it felt a little sparse compared to the rest of their data, but it was, overall, this is very interesting.
Yeah.
I mean, as a synthetic test, it's very similar to the other ones. It's just with slightly different constant factor difference of the latency. So I'm not really surprised they didn't try to replicate the full test suite with it.
So now that more folks are here, Mark, did you already kind of give an intro and everything?
I just, not exactly. I just basically said I liked it, more or less. I thought it was a good paper. I mean, the only the nit that I kind of had with it is that they're testing this on a really complex NUMA architecture, and they did do a good job of like isolating it, right? They were kind of aware of that, and they even said in here that that even when they were crossing NUMA nodes, that they could still get good performance with their solution. So I mean, that was impressive to hear, honestly. But yeah, that was kind of my high level takeaway from this. I mean, Josh, what did you think? What was your thought on this?
Yeah, I thought the main piece about like treating throughput and latency sensitive applications as entirely different classes and being able to consider the cost of rerouting versus the cost of head of line blocking and other pieces is a pretty important concept.
Yeah.
Do we want to summarize what the paper actually did for people who didn't read it? So at a super high level, the paper describes two application classes, as Josh mentioned, LApps and TApps, which is, I think a classification that exists prior to this paper. LApps refer to applications that submit relatively small number of latency-sensitive IOs. TApps are apps characterized by trying to get as much throughput as possible. They're sort of classic batch versus transaction processing stuff. So the comparison here is between the default Linux, or the current default Linux block queue implementation, where each core has its own queue for IOs coming from that queue, and the IOs filter through those queues on a per core pinned kernel thread down to their respective device IO drivers. With classic Linux, with the current Linux implementation, this behavior causes IOs from TApps to tend to block at the head of that queue. Apps from LApps resulting in poor latency for the LApps and surprisingly not that good latency for the throughput for the TApps. This paper's contribution is adding per core ingress and egress queues. So each core submits to its own ingress queue for LApps, or to its own egress queue for LApps, but for TApps, it's free to rehome to a core that is less utilized. So the key sort of pattern here is latency sensitive stuff goes to the local resource, throughput sensitive stuff moves to wherever there's room. Because the latency hit in swapping cores is pretty trivial compared to the throughput gain by utilizing unused resources.
I think the other major piece there was
a good summary.
Yeah, that was a great summary, Sam. I think another major part was separating those two apps into different queues so that they could prioritize the egress queue for LApps when there was any kind of latency interested applications operations in flight.
The paper even does a pretty good job of demonstrating the difference in effect from that prioritization alone versus that prioritization plus the multi-core rehoming thing.
Who is
Yeah, I
responsible
think
to
that.
break down into T-apps and L-apps? Is this application classification? What happened with applications which can do both?
This
They
is an
can do
artificial
latency.
application specification used elsewhere in the literature as well. No, to the extent to which this reflects a real system is perhaps debatable, but you sort of accept their classification at face or as a given for this analysis.
Yeah, I mean they're not even using the same apps across like SPDK and the traditional stack, right? I mean they're using like their SPDK's perf benchmark for that versus FIO or the other one. So I mean, yeah, you just accept it or you don't, I guess, right?
Yeah, I think that they do touch upon that the TApp and LApp is an oversimplification of an app profile that could be extended to be more complicated. But I think the general idea that I liked was that the three mechanisms that they touch upon and how they interplay and why each of them are important and how they demonstrate that bit was very, very impressive.
Yeah, I agree.
Did you guys see the note in here about how it actually kind of counterintuitively improved as they added more load?
Yeah, but that's going to happen with any system. They're just explaining why the graph does that, I guess. You made a comment earlier, Mark, about you were surprised that SPDK's numbers were bad, even though they ran a test that should have worked well for SPDK. Which one was that?
Let me see if I can figure it out. That was by recollection. I didn't write it down, which I should have.
As far as I can tell, every one of these tests involves at least one LApp and one TApp on the same core. SPDK is never going to behave well then.
Oh, maybe I was misinterpreting it because I thought that they had run something where they did that, but I might have inferred that and been wrong.
Yeah, this would actually be a cleaner analysis if they'd skipped the SPDK thing entirely. Because what they're choosing to do here is they correctly observe that if you try to run multiple things, one of which is SPDK in the same core, whatever the SPDK app is doing is, one, going to suffer severely versus if it had the core all to itself by design. Secondly, it's going to destroy the performance of anything else in that core.
Yes.
Because it's
Absolutely.
going to always occupy its entire time slice. It's never going to give the core back of its own accord. So basically all of their SPDK bars can be interpreted in that light.
Yeah, it's essentially don't use SPDK in this way. It's not designed for running with other applications in the same place.
I mean, it's a valid observation for this paper because they're trying to make an argument about the Linux I/O stack. So, and aside of, by the way, SPDK doesn't magically fix this, is, worthwhile. But I'm not sure they actually needed to bother evaluating it like this.
That seems almost more like maybe I don't want to say backhanded way, but a little bit of a way to make their numbers that much more impressive, right? By including SPDK in a bad way.
It's kind of nice to have, I guess. It's kind of nice to have some quantitative measurements of exactly how it behaves.
Sure.
There is an LApp latency hit, incidentally, from using the system at all. It's hidden a little bit in the log graph they're tending to use for latencies, but they note it down in one of their sections below. The increased complexity in code path does cost some time. And I'll also note that this configuration is highly unusual. Most users aren't going to try to maximize usage of all of their cores across this heterogeneous an application paradigm, right? Like, for this to make sense, your organization would have to be your organization would have to be trying to run like many different applications on the same host with very little control over what they're doing. It
Yeah, it
could
sounds like
make
a
sense in a
description of
public
cloud
cloud
computing in
sort of
general.
environment. Yeah. But even then, you tend to get cores to yourself. Even with this system, for a variety of other scheduling reasons, you're going to suffer serious latency degradation from allowing them to run on the same core in the first place. So I'm not even sure about that. For public cloud situations, this basically implies the just absolutely no resource isolation.
I mean, they didn't here mention L3 cache contention, unlike a given like socket, right?
They have mentioned that they experience severe cache contention on level 3, just
Yeah,
running
it's under.
higher number of threads.
Yeah, this was 5.2 under section 5.2. They talked about it a little bit.
So I have thoughts about how this applies to Ceph. Talk about that.
Yeah, go for it.
So everything I just said about applications typically not sharing a host is very not true of Ceph. OSDs do typically get IOs from a variety of different applications with absolutely no control over where they come from or what messenger thread they come in on. It's also not uncommon for deployments to mix Rgw and Rpd workloads, where Rgw would be very much like this sort of T application sort of situation. Rgw is latency sensitive, but not in the same way that individual IOs from Rpd are. And Rgw tends to bulk writes in a way that Rpd does not. So some of these tricks, if they could be applied to Rados, would be very valuable. Of course, the IOs coming in would have to be tagged as such. But we could do that. That's not that hard, actually. So an interesting question is, how would we apply this technique to Crimson, for instance? So we've been sort of assuming that in Crimson that we're going to pin PGs to cores. And that's for a good reason that is specific to Crimson and very different from the situation presented here. Here, these IOs are essentially context-free, or they don't have they're stateless.
They don't have ordering.
They don't have ordering, but more importantly, the device drivers don't do anything but apply some extremely minimal processing and forward them directly onto the device stack. There's no state maintained by the device driver that needs to be. There's nothing analogous to a PG log, for instance. There's nothing there's no caching to do. There's nothing of complexity at all. This all happens below the caching layer. So it'll be a little bit more difficult for us to apply these lessons. But in Crimson, if we could arrange it so that the portion of CStore that's responsible for actually dispatching IOs is able to freely rehome PG state across cores, then it would be possible to set up something where PGs submit locally for IOs that are latency sensitive, but we tend to rehome to underutilized cores for ones that aren't. So this does provide us with with a great deal of work. This framework is actually probably a pretty good pathway to getting good load balancing across reactors in Crimson, with the caveat that it has to be the case that it's very, very cheap to move the state associated with a PG from core to core for CStore.
I also see that particular groups of PGs or pools in general are more commonly used as throughput or latency sensitive. Like,
yes,
for example,
that's correct.
in Rgw, the data pool is obviously going to be more throughput, and the metadata pools may be more latency, like for the bucket index pool, whereas other metadata pools like garbage collection and logging may not be, maybe more throughput as well. So I wonder how much we would need to be moving PGs around across cores as opposed to kind of grouping PGs appropriately.
It's a matter of scale, right? So the advantage of this system is you don't need to pre-group them. And
Right.
As utilization changes, you can rehome these. You can rehome IOs with individual IO granularity. with only a very modest hit to latency here, and whole applications with only somewhat more. There's a section on that where if they find that a single core is too overloaded, they'll start rehoming the TApps on that core to a different core so that they don't have to do as much steering. That would be the analog there would be moving the sort of default home for a PG from point to point.
Right.
So I agree.
I wonder in these tests if they had any consideration for locality of the NUMA nodes and the underlying storage devices. Like if you do that on a massive scale and you're moving stuff to other cores that are across NUMA nodes, at some point you could imagine that stops being a good idea.
You'll notice that their very large-scale problem actually involved a remote NVMe device.
Mm-hmm.
Yeah, I'm not sure that we would have had seen those like NUMA affinity effects other than at the network side for these tests, because they were running like against a null RAM block device or against like a remote SSD, if I remember correctly.
Mm-hmm.
But it's a pretty simple extension, right? Any core that isn't local to that device always does the remote egress thing.
Yeah, the cost of switching device is high enough that would make sense.
Well, you're literally required to. You can't submit it locally.
Oh, I see. Right.
I mean, it's a misconfiguration, but in a way, this whole paper is about a misconfigured host, where you either can't or choose not to do any kind of resource static partitioning.
Going back to the idea of how this applies to Ceph or Crimson, especially, we also have a number of constraints in terms of our processing and for op ordering. I'm wondering how that, I guess if we're talking about per PD scheduling, it's and purely choosing which PDs to run next. That doesn't matter so much. Sam, I'm curious, what do you think about the idea of having latency sensitive versus non-latency sensitive PGs, and I think that the prioritization that they apply, where they always process latency sensitive operations if they exist.
We don't have any ordering constraints that prevent us from changing the ordering of ops between PGs.
Right,
so
right.
We could already do that. In fact, that's essentially, we try to do that, at least the way DM clock currently works. We try to do this by prioritizing ops as they go into the PG. But in principle, we could do the same prioritization again between the PG and the object store.
Mm-hmm.
We mostly figure we shouldn't because there's no real reason to keep that much queue, but we could. Does that make sense? With this concept of some kind of dynamic queuing between cores, it would happen by default. C-store's queues would be multi-queued. So yeah, it would be possible and in fact normal for. I mean, I hesitate to even say it would be processed out of order because the reality is that there wouldn't have been any order implied in the first place. So.
Right. I guess I'm wondering why you're suggesting that we want to do it at the object store layer as opposed to having the scheduling in a single place, kind of integrated in with the DM clock scheduler in some way.
It is. So the question is, which state is cheaper to move? So the in-memory state associated with the PG is pretty expensive, and we do a lot of allocations. So one of the wins of using C-star in the first place is that allocations for the most part will be reactor local, and won't interact with the rest of the system, with other cores, I should say. By contrast, depending on how C-store's design ends up working out for multi-core, it might be very cheap to move the PG state between cores. As in, there might not be that much allocated state per I/O.
Mm-hmm.
So it's a matter of that. It's really a matter of that. Another way to do it would be that you simply move the PG state to whichever reactor receives the message up at the top originally.
Right.
But it creates more contention. Do you see what I mean? In general, like this system works as presented in this paper because there is no state associated with
there's
with
very
these
little
jobs. It
switching
makes
cost.
no difference. It's just a matter of which thread does the actual hardware poking.
Yeah.
Really. But with the PG state in an OSD, there's a whole bunch of in-memory state, a much of which we actually mutate. And there are interop dependencies for writes, not so much for reads, but for writes.
Mm-hmm.
And there are write-to-read dependencies. Reads have to see the state that writes just created. So that limits our ability to simply process an op in whatever core we want to.
Right.
If you're talking about prioritization, that's different. But we plan on doing that before it goes into the PG anyway. The advantage of doing it before it goes to the object store is that is basically limited to the case where we want to be able to reroute an I/O to an underutilized core. Does that make sense? I think I think that's the question you were asking. There wouldn't be much point in doing a second layer of prioritization if we weren't also rerouting.
I'm not sure I understood your last sentence exactly. Can you?
I think you're right. There isn't much point in doing a second round of prioritization between the PG processing and C-store processing stage unless we are also rerouting to another core.
Because at that point, we're already paying the higher cost of rerouting, and therefore it may be worth the extra switching cost at the C-store layer as well.
Well, the entire point of sending it to another core was that that core is underutilized. So we wanted to make scheduling decisions locally at that core, not on the core it came from.
I see what you're saying. So you're offloading the scheduling processing to that less utilized core at that point.
You're offloading processing of the op itself, the C-store part, the part where we, do IOs, do reads, do writes, that kind of thing.
Right.
Process the LBA tree, that kind of thing. The overhead of doing that handoff is felt by both cores, as observed in this paper. I don't know if any of that's actually worthwhile, because you'd have to know that the PG state being accessed there, the root, wasn't being used on any other core, which implies a level of inter-core communication that I think we don't really want. But that's what occurred to me as what a system like this would look like in Ceph. Other elements, of course, that probably just always make sense are this sort of tagging of IOs so that we know how to treat them. But I think we already knew that.
Tim, as you're talking about this and thinking about this, as I've thought about Crimson in the past, my thought has always been that we would have like a local queue for local handling of IO, and then some kind of export queue for other shards to handle an IO or request that came in that wasn't local to it. Is that more or less kind of what you're also describing here, or am I mixing up things?
That's just like how the messenger has to work for now.
Yeah,
because
but what I'm getting at is, go ahead.
I'm just saying that's just a basic description of how the messenger has to work right now. The messenger does have to hand off IOs to the core that's supposed to handle them.
The reason I bring it up, though, what I'm getting at is are we going to really end up in a lot of situations where we are handing stuff off to other cores and we don't expect them to already be well utilized?
I'm saying that this paper is an argument that situation is common.
Is it with us, though?
I don't know. You can preface everything I said with assuming that our system actually exhibits these behaviors and it's worth the implementation cost and the additional state that we would have to maintain isn't too expensive. This is hypothetically one way of doing that.
Sure.
I guess that's the fairness part. Is also we're thinking about the prioritization pieces, maybe independently, as how would we design C-store and Crimson for being able to get low tail latency?
In the sense that we want to design it for low tail latency? Sure.
Yeah.
I mean, that's a big question.
I mean, it's that part of the scheduling that we haven't really addressed at all yet. ITM clock is primarily about throughput, not really considering the different classes of applications in terms of latency guidelines and what they require there.
DM clock is sort of assuming the two things are the same thing, which
yeah.
isn't actually an unreasonable assumption. Again, as Gabby, I believe, pointed out earlier, this L versus T distinction is an artifact of this analysis.
Yeah.
It's sort of true, probably. There probably are really applications, there probably are domains where this classification is valuable, but I don't think it's ever strictly a binary. And I don't think there's any requirement that a particular application is always one or the other.
No, I think the nice thing about their implementation here is that they're talking about like a application and treating it on a per thread basis, so you can have a different profiles for different threads.
Yeah, sure. But even, I mean more of a time varying thing.
Oh yeah.
Where at times an LApp that just starts to become overloaded is a TApp. Because its own resources are going to be stretched anyway, so its latency will be shot to hell. But it'll still be able to conflict with every other LApp on the system. Right?
Didn't we have a similar challenge anyway, because we handle metadata and the payload, and the payload usually is multiple times of the metadata that we handle?
I'm sorry?
I said we have a similar challenge because we handle the payload that is multiple times the size of the metadata that we need to handle on for the same device. So we have a similar challenge that we mix up both IOs just in the same core, perhaps.
Yeah, but they're not independent. The idea here is that the LApp IOs and the TApp IOs are, for different apps, are actually distinct. When we're processing the metadata and data for the same IO, they're dependent. We can't process one without the other. So similar in the sense that we care about the latency of the whole operation, but dissimilar in the sense that they can't be separated.
But as far as I understand, the what they say, the application separation is done by threads. So people would be able to separate this by threads. So the payload and the other one, will it help, or would it be?
No, they're separated by threads because the tagging is done by threads. But when they say 3 LApps, they mean 3 totally independent, unrelated applications. Does that make sense? So if at some point in time they simply need to process IOs from those 3 applications in order to satisfy their latency requirements, they can actually do that. They don't have to process anything from the TApp, except that it would destroy the TApp's throughput. But if we're talking about, again, metadata and data for the same IO, it doesn't matter if you separate them across threads or it doesn't matter what you do. The IO isn't complete until both the metadata and the data for that IO are dispatched to disk.
Yeah, sure.
So it's fundamentally dissimilar. Yeah.
So it would help only just in terms of contention on the core itself.
Yeah, sure, they create contention, but we can't solve it in any of these ways. We have to actually, it's only contention in the sense that the same unit of work pulls from multiple resource pools. We can't separately schedule the 2 resource pool pulls.
So are we saying, if we have to map the concept of app back to Ceph, are we saying that we cannot be doing that at the RGW op layer. It has to be like the OSD op layer.
No, I'm saying that, for instance, in BlueStore, it probably wouldn't be very useful to use this subsystem and tag the sync thread as an LAP with the bulk write piece as an LAP, because you'd still be bounded by the slower of the two.
Yeah.
So it might seem like you could, because the write streams have this like superficial relationship, or the superficial resemblance to these two classifications, but because the IOs being performed come out of the same queue, and they are dependent, it won't actually help the application level latency. In fact, it will probably destroy it, because the system will be incentivized to process the sync thread at the expense of the actual IOs.
Yeah, going back to the RGW example, like an RGW write that needs to update the bucket index and write to the data, it's also not complete until it does both of those things. So I think both those ops would have to, you'd want to treat those as latency sensitive.
Yes, that's true. So I just meant that doing it under the OSD without considering the actual op in the client isn't very useful. You'd need the prioritization would have to be at the like op itself layer, or up at the
client
RGW, original RGW op, or tags coming from the original RPD application.
And just trying to map again concepts back. So like they talk about request steering and application steering. So what would request steering in Ceph look like? Or would it even be a possibility given that request would be at a PG level? Or what are your thoughts?
I mean, that's kind of what I was describing before. So at a basic level, it's so the concept would be this thing where within an OSD, we attempt to load balance requests for throughput sensitive stuff across all available resources. Obvious resources include cores, but also if CStore is managing multiple devices as well. We might have multiple submission zones in a ZS device, for instance. Well, the challenge is that for Crimson, there's a bunch of state associated with a PG that we need to both read and mutate during the we need to mutate it during the process of processing a write, and those mutations need to be reflected when we're processing a read. So the only ops on a single PG that we can theoretically perform without synchronization are two reads. But in general, no. Once you processed an IO on a core, you probably need to process any other IOs for that PG within a short period of time on the same core.
Yeah.
Because otherwise we'd have to deal with inter-thread contention, which is unlikely to be a win from a latency point of view.
Yep, makes sense.
There's a similar relationship with CStore, because a sort of functioning assumption has been that each PG or group of PGs will get its own root, metadata root, with similar requirements. We need to do reads need to see recent mutations, and mutations need to mutate that state. So assuming that it's expensive to move these things between cores, the answer is no. You pretty much have to route the op to the core that's supposed to handle it. The application steering component might be of some interest. If ops coming into a PG tend to be TOps, as in this classification, we could make a point of making it cheap to move the core responsible for a PG, that we get a good distribution of those over time, even as the load profile changes. That idea might be the easiest to apply.
Yeah, agreed. Yeah.
What is our plan right now for being able to allow steering of requests over the network to specific PGs that are running on different cores? Do we have any ability to do that?
No, we've talked about ways of doing it. It's pretty unrelated to this topic, actually.
How so? I'm not seeing that.
It's static. It would actually further constrain our ability to move PGs between cores. because we'd have to expose that assignment out to clients.
Mhm.
So there would be no dynamism to it at all. There wouldn't be any steering as such. Again, this paper isn't just about steering I/O. It's about steering I/O based on underutilized cores.
Yes.
Or
So, yeah,
underutilized
the thing to
devices,
talk-
as you mentioned before, too. Like, that's another dimension that I think they didn't cover in depth in this paper, but talked about maybe covering in
Nevertheless,
depth in another one.
a time varying resource
Yes.
usage, right? Which
Yep.
is the exact
Yeah.
opposite of what you'd want if we were exposing these things out through the OSD map, which is what you'd have to do. You'd have to say, we're running messengers on these ports, use this way of determining which port to send it to. If you want it to be compact, or you could have an explicit mapping of PGs to OSDs, or to cores. But either way, the scale on which you'd be willing to update the information being given to clients would be vastly smaller than any kind of resource utilization imbalance. So it's
Not
really
convinced that's necessarily true. It could be you could have long-term imbalances that last for minutes or hours, and then
yeah.
it
So that's what I was saying. It's possibly applicable to this long-term imbalance thing, but we'd have to be willing to do an explicit mapping in that case because it's unlikely that those imbalances would map neatly to some kind of simple round-robin assignment. And I don't think we're going to be willing to put 150 PG to core assignments per OSD in the OSD map.
Perhaps not the OSD map itself, but we could think about a different mechanism for those clients that are talking to that particular OSD, perhaps.
That's true. It could be part of the initial handshake. In which case, yes, that would be that could be doable. That could even work on shorter timescales.
Yeah.
It's a pretty good argument for not putting in the OSD map.
Just make a general map that we don't need to update the clients all the time in terms of their software version.
I mean, I think if you're willing to do it in the initial handshake, it's not that expensive to just give an explicit list.
Yeah. Updating it over time, I guess.
Yeah, exactly. Or any time a client sends an I/O for a PG on the wrong core, you just say, by the way, PGX is on this core.
Yeah.
That might be even easier. Either way, it's sort of orthogonal. That's more about coming up with a mechanism for informing clients about this PG to core mapping.
Right. Is it worth considering this kind of steering at a higher level, like when talking about overloaded OSDs or hosts entirely and switching data to different racks or different hosts?
I mean, that's basically what the imbalance doohickey does, right?
Well, today it doesn't do anything related to performance or load.
No,
it's really about
for
capacity.
Storage size. Yeah.
Yes.
But same concept. Like that's what that mechanism is for.
Right.
But I'm almost willing to say I do not think it is possible that we ever want to move data based on a transient imbalance in I/O. So the timescales involved would have to be hours.
Yeah, it'd have to be quite significant to be able to make it worth moving that much data.
And because of the way pools and PGs work, it's sort of unlikely that you're ever going to get an imbalance like that. That isn't also related to size. Because the assignment of logical blocks for RBD or objects in Rgw to PG is pseudo-random. So the probability that a particular piece of hot data is on a particular OSD is proportional to the storage on that OSD. So possible, but unlikely.
Are there any background tasks that would potentially be impact that we might temporarily want to route around?
We probably wouldn't move data for a background task.
Sorry, not move data, but have like incoming work coming in on a different like messenger on a different core that potentially would be non-local to wherever the work would end up being done. Does
Yeah,
that make
that makes
sense?
sense in terms of like talking about like these, like, so for example, like Rgw GC pools or other sorts of TF type of background apps where you're trying to group together those PGs to like specific cores so that they don't impact the LApps on the other cores, right?
Yeah. I mean, I was thinking like the equivalent of like I don't know if there's some kind of like RocksDB like compaction happening on one or something along those lines. I mean, I know it's not C-star or C-store, but just something that's background work that's happening. Maybe you temporarily want to have incoming requests coming in on some other core that's also in
The
the same
problem
unit
with that,
node.
though, is all of the stuff I described about why you can't just process an op on another core. So you could move the messenger handling portion, but I don't think it would be worth it.
Unless you want to
Okay.
move the rest of the handling too.
Yeah, so the more natural way of doing this would be to not have very many PGs on a core and use that core for background stuff.
Yeah.
Or just no PGs on a core and use that core for background stuff.
Sure. I guess this paper's argument then would be that when background stuff isn't happening, that core is just sitting idle. But
which means we could rehome stuff back. But again, unlike this paper, we do have state.
yeah. Agreed.
And so I guess one of the big takeaways for me is from this and Ceph is we probably should be thinking about considering like different pools or different PGs or even different requests potentially as and treating them differently based on their latency requirements in order to lower the overall latency and if we do steering, eventually increase throughput.
I mean,
So Josh, the high level idea would be like we determine which pools belong to which class.
Yeah.
Mm-hmm. Yeah, I think I mean, the general idea about classifying pools into different, talked about it, I think in one CDM. The goal was not steering, but I think the goal was setting different performance profiles for different pools, right?
Right.
But yeah, that in general might be a good idea to even start with classification and then decide how we can use that classification.
Yeah, exactly. There's also one, I guess, if we're doing it like, based on a PG, maybe it doesn't matter so much, but it might be interesting to look at for RBD where we're only using a single pool. Is there a meaningful distinction? It could be just maybe based on request size.
It would be based on some kind of an OCS Kubernetes level classification of the application itself when you do the initial mount.
Yeah, so that could be like a property of the image itself or something.
Obviously.
Josh, what would be the advantage of doing it on a pool basis versus tagging the I/O?
Well, everything we talked about with the steering aspect requires us to be treating PGs independently. Talking about steering IOs within a pool, that's quite different.
So the first problem is the word steering. We can't steer IOs. IOs have to go to the PG. They're to the pool
Right.
therefore. They have to go within that pool to the PG therefore. And for the reasons I outlined, they have to go to the PG core that they're for. So the only thing available to us is really moving PGs between cores. So if the pool as a whole has some kind of tag as to whether it's an L or a T pool or some other classification that's slightly more descriptive of what really happens, then the OSD can be slightly more deliberate about arranging those PGs across its cores. Is that a good summary, Josh?
Yeah, I'd add that I agree that that's a good summary of the steering aspect, but I think the prioritization aspect could still apply potentially within a PG, if we're classifying.
Prioritization actually can be per IO though.
Yes, exactly.
That's yeah.
Okay.
But then what's the advantage of doing it by pool if you can do the prioritization by
Well, the
IO?
prioritization gets you only some pieces. It lets you, like the paper showed actually in their implementation, it enables you to drastically reduce the latency, but at the cost of throughput. So the steering is what really enables you to get the throughput back after you're prioritizing the latency by processing the latency sensitive requests first.
To be honest though, I don't think we can use that kind of steering is essentially unavailable to us.
No, yeah, not at the request per request type.
Yeah, just the application steering on its own will be able to handle imbalances on a much longer time scale, but that's it. It means that if we choose to get, or if we get a latency sensitive op on a particular core, we can't just in that moment redirect all the throughput somewhere else. We have to process them locally, so they will take a throughput. I really think that was a core piece of the secret sauce here. There's a latency hit to changing cores, but only a very small one. So it really is basically free for them to do this literally every time there's an imbalance.
Yeah.
Yeah.
Are there other thoughts on the paper in general? Not necessarily anything related to Ceph, but other takeaways?
Questions?
In general, yeah, just about the paper. I thought it was a well-written paper. A lot of papers, it's not very intuitive to like understand the graphs, and they did a pretty good job of like mapping the text back to the graphs. So it was very clear as to what they are trying to present. There was not one unnecessary, graph that people would have ignored, which I believe is a win for the authors. In that sense, I thought it was a good paper.
I thought this paper was superb. I'm really glad you suggested it, Josh. I think that this is just going to be part of my mental framework in dealing with resource balancing forever.
Yeah, I think it was really fantastic. It had a number of citations that looked like they could be pretty interesting too, in terms of more recent papers relating to trying to deal with latency and multi-tenant aspects.
Yeah, actually, Josh, that was one of my favorite parts, was actually just looking through the list of like 52 citations, right? It's like, holy smokes, look at all this.
Yeah. I haven't really been keeping up with a lot of the literature the past several years, so I think there's a lot of interesting nuggets we could glean from some of these papers.
Yeah. Well, one thing I always think about in terms of these papers, though, is like, I wonder what, if anything, will actually come out of it for real, like in the kernel, right? Like, will we ever see any of this, or is it just going to kind of go and be lost to time?
Yeah, that's a good question. I mean, their implementation is certainly pretty researchy in terms of not being like it's like relying on the NVMe over TCP stuff and modifications to the block layer, and it's not necessarily designed to be directly used in the kernel for protection, but I wouldn't be surprised if folks got inspiration from things like this and things like that, and eventually the kernel saw improvements to its block layer and scheduler.
I think the biggest impediment to this is what I described before, which is that I'm not sure that this actual deployment scheme is ever actually a good idea. So the pushback might be that this is it's trying to optimize a case that really shouldn't happen in the first place.
Well, you say it shouldn't happen, but it's such a common case today in terms of even private cloud deployments where like,
all of the apps are IO bound?
Not necessarily that they're IO bound, but that they're resource bound in some way, right?
I mean, this only addresses IO though. You would have to do the switch for every one of those resources. And it would have to be the case that the resource is actually routable like this. This is in some ways kind of a magically special case where in a way, this processing that's happening, that thing that we're optimizing for, doesn't need to happen in the first place. If the applications were submitting directly to the device queue, then this wouldn't even be a resource to contend on. And I think that observation is core to why this works in the first place. There's no state on each core associated with the I/O. There's nothing that the core actually does other than translate from one thing to another.
Yeah.
So any situation where that's true will very likely also be a situation where you can eliminate the step entirely. I do hope it gets merged, though. It's a pretty unambiguous win. Or I hope someone takes the time to put it into a state where it can be.
Mm-hmm.
All right, well, we are at the end of the hour, guys. And I think we'll just have another meeting after this. So any final comments from anyone?
Oh, wait. Networking almost always falls into this category. I hope this happens to the networking stack. That's my last thought.
Yes, agreed, Sam. Actually, right before we go here, how does the current networking stack work? Does it do anything special, or I don't know. I don't know if they talked about that in here at all.
Yeah, I don't remember details about the networking stack part of it. Not sure if they were doing, and they had a bunch of optimizations enabled, and they're using some pretty fancy NICs. But beyond that, I'm not sure. They did reference an interesting paper that was talking about how to achieve very low latency with TCP, kind of contrasting that to RDMA, and suggesting that you don't need an RDMA set style protocol to get those kinds of benefits. That might be interesting to take a look at.
Yeah, definitely. If you find that, Josh, put it in the list here. All right. Well then, have a great week, everyone. Thanks for coming. It was nice to see so many faces. And see you next week.
Bye-bye.
Thank you. Good discussion.
Thanks.
Thank you.
Yeah, and
Was
thank you, Josh,
interesting.
for
Thanks.
finding it.